Hi, my name is Alyssa Jankowski, and I did my honors video on hierarchical galactic formation. So it's been 13.8 billion years since the universe was born in the Big Bang, and it certainly doesn't look like it did back then. Back then, it was a crunched up ball of very hot particles which expanded out and cooled down over time. But that's the cliff notes of what happened. How did the hot particles become planets and galaxies and people like us? That question is answered by the lambda-CDM theory. The lambda-CDM theory states that the universe followed a hierarchy of creation, wherein clouds of dust and gas created nebulae, and the nebulae made stars, which made star clusters, which made galaxies, which made galactic groups, which made galactic megastructures. The brunt of that creation, though, falls on two things: gravity and dark matter. Of course, the force of gravity is familiar. It pulls things together. You drop an apple, it'll fall towards the earth back into your hand. Now, dark matter, however, is a bit more of a foreign concept. Dark matter is matter that we cannot directly observe. Unlike antimatter, dark matter is similar to normal matter. It just doesn't interact electromagnetically, meaning that we can't observe it with light. Unfortunately, since most of our observations come from the electromagnetic spectrum, or light, dark matter is a bit of a fickle thing to observe. Thankfully, this is where gravity once again comes in to save the day. What we can see from dark matter is how it affects the orbits and motions of other objects, including light. Light emitted or reflected by those objects bends around the dark matter because of gravity, showing us motions that we can't explain without dark matter. We can observe the impact of their impact from the first moments of the universe, seen in the cosmic microwave background radiation, or CMB. Our ability to find dark matter tells us that there is a lot of it in the universe. However, the lambda-CDM theory focuses on a specific type, cold dark matter. The CDM part of the name lambda-CDM. We're not really sure what cold dark matter actually is, whether it be primordial black holes, or weakly interacting particles called WIMPs, or axions, or what have you. But what we do know is that it probably accounts for much of the gravity in our universe. So what does this all mean for Earth? In the short term, honestly, not much. However, what this does allow astrophysicists to do is puzzle out what will happen in the long term. Astrophysicists believe that the Milky Way galaxy will slowly begin to merge with all the other galaxies in our area, starting with the Andromeda Galaxy. These mergers will create a spectacular fireworks show in the Earth's skies as nebulae in the galaxies merge and new stars are born, as you can see up here. However, all good things come to an end, and that includes the universe itself. There are a few theories as to how the universe will end, like the Big Freeze, in which all stars eventually burn out and all that's left is black holes, until those eventually decay, leaving nothing behind. Or heat death, where the universe reaches maximum entropy, meaning that heat is evenly spread throughout the universe. And there are many other theories, including my favorite, the Big Bounce, in which the universe crunches back into a state like in the Big Bang and bounces back out again to make another universe. Now, the fun part is that we don't really know how the universe will end. It's all speculation. So you can take your pick on your favorite. What we do know, though, is that dark matter is incredibly important for the overall development of the universe, and that we couldn't be here without it. No matter how the universe actually ends, or what galaxies smack into the Milky Way, or what have you, we existed, and that, in my opinion, is one of the coolest things that dark matter has done. Thank you, and have a good day.